Hi guys. Yeah, put my floating head over here. Okay. Hi everybody. So for notes today, we're going to be on page number 10. This should be a pretty short video. There's really only kind of one topic that we need to talk about, and then we are going to just finish the summary of bond types that we started on page number 11. So let's talk a little bit more about covalent bonds. Previously, we had discussed that a covalent bond is when there is sharing of electrons, right? Well, think about how you share things. When you share things, there's two ways that you share it, right? Like if you are sharing a cookie with your best friend, like one of those big chocolate chip cookie situations, it's your best friend, right? Of course, you're going to cut the cookie exactly in half and give half to your best friend because you like them and you want to be equal. And then there's the way that you share something when you're forced to share with like a younger sibling, like, you know, your mom's telling you like, oh, you got to share the bag of popcorn at the movie theater or whatever. At least if you're anything like my children, what that means is that my older child will take like 3/4 of the whatever it is that we're sharing and give like the scraps to her younger brother. So that would be unequal sharing. Yes, technically they're sharing. However, it is not a 50-50 split. The same thing is going to happen with electrons when they're being shared. And it depends on the strength of the electrons. How much affinity do those two, or not, it's not the strength of the electrons, the strength of the elements that are making the bond. How much affinity do those two elements have for those electrons? If both atoms are equal strength or electronegativity, then they will share equally. The further apart those two elements get in terms of their electronegativity values, the less equal the sharing is going to be. So when you have unequal sharing of electrons, that is known as a polar covalent bond. So unequal sharing of electrons. And this happens when atoms have different electronegativities. So if you are looking up the electronegativity difference and you wind up with something, an electronegativity difference of 0.1 to 1.6, that would be unequal sharing. And the atom with the higher electronegativity pulls the electrons closer to itself. So let's take our example of water. So I'm going to draw water really quickly. We know now water has that bent shape, that 104.5 degree bond angle with the two single bonds from the oxygen out to the hydrogens and then 4 unbonded electrons. Okay. Well, if I look up electronegativity values for these elements, I look up oxygen. Oxygen has an electronegativity of 3.4, and there's no unit on electronegativity, right? Hydrogen has an electronegativity value of 2.2. So oxygen is more electronegative, which means the electrons that are in this bond between the hydrogen and the oxygen are going to spend the majority of their time around the oxygen because oxygen has the higher electronegativity value. It's stronger. If they were in a tug of war, oxygen would win. So it results in what are known as partial charges, and your molecule is now referred to as a dipole. It's a molecule that has positive and negative regions due to uneven distribution of electrons. Now, to be clear, though, these aren't full charges like what we get with ions. With an ion, a positive ion or a negative ion, the electron literally leaves one atom entirely and goes someplace else. So it is a permanent charge, a permanent change in charge. With these dipole molecules, you get partial charges where the electron is still sometimes going to be found around the hydrogen. It's just spending most of its time near the oxygen. And there's a couple different ways that we can show this. So if you're ever asked to show partial charges, there's really 2 different methods. The one method that people will use is parallel to the bond line, they will draw an arrow. And they point the arrow towards the element with the higher electronegativity value. And then on the back end of the arrow, you kind of make a little cross line to turn it into sort of a little plus sign. So what this means in terms of charge is that the oxygen is partially negative because the electron likes to be there more and electrons are negative, and the hydrogen is partially positive. Now the other symbol that you're going to see, and you can see it right over here, right next to this H and this Cl, is it's a Greek letter delta. And I want to show you how to draw this nice and big in case you're unfamiliar. So what you do is you start by kind of drawing an S, and then you curve it over into itself. That's the Greek letter. It's a lowercase delta, not to be confused with an uppercase delta. So in my head, I refer to this as the pirate hook because, you know, I'm a child. So what you would do is you would draw a pirate hook negative next to the oxygen and pirate hook positive next to the hydrogen. That's another way of showing partial charges. So if you're ever asked to show partial charge on something, you can either use the arrows, where you're pointing the arrow towards the atom that is more electronegative, or you can use the partial negative and the partial positive. You'll see both, okay? When we have equal sharing, that would be called a nonpolar covalent bond. Equal. Okay. So when equal sharing of electrons is nonpolar, causes there not to be a positive and negative region. There are no partial charges formed between atoms having equal or pretty much close to equal. So your electronegativity difference is 0. This absolutely happens anytime we have a diatomic molecule, so H2, O2, N2, any of those, where you have this equal sharing. You can see there's no partial charges there. So these are just two examples. This one on the right, this would be a polar covalent bond, and this one on the left is a nonpolar covalent bond, okay? Now there is also another type of covalent bond that can happen known as a coordinate covalent bond, which is a covalent bond that forms when one atom contributes both bonding electrons. So typically when we think about sharing of electrons, you get one electron from one atom, one electron from the other atom. But there's exceptions to that rule because there's exceptions to everything, right? We're trying to apply man-made rules onto natural processes, and that doesn't always work 100% of the time. So if you're ever trying to, especially for some of our polyatomic ions, like if you were trying to draw out a Lewis dot structure for hydronium, H3O+, or ammonia, NH4+, and if you were trying to figure out, like, how do I draw this thing and where are the electrons coming from, it's not going to work out the way that you think it's going to work out, because in some of these polyatomics, when you're making a single bond, both of the electrons, rather than going one from one and one from one and bloop, you have your atom over here and your atom over here, and both electrons are coming from one atom to form that bond. So it's just a special situation worth mentioning as you start to get into more complicated molecules outside the scope of this class. You might run into that situation of like, it doesn't make sense. I'm circling stuff and it doesn't make sense, because it might not. There's exceptions. Okay. So just to throw that into the void. So we filled out part of this chart already. We already did the ionic. See it in the corner there. We already kind of talked about the molecular and network solids. What I'm going to fill in now is this top part where it says covalent. The first thing I'm going to do is change the terminology here because that's a typo. Where it says polar molecule, nonpolar molecule, I want you to cross that out. And I want you to replace it with polar covalent and nonpolar covalent. Okay, when we're talking about bonds. So when we have a polar covalent bond, that would be between two different, I'll just say two nonmetals. We'll go with that. Typically, well, always, they're going to be different nonmetals. So you have unequal sharing. So an electronegativity difference of 0.1 through 1.6, okay? With nonpolar covalent, it's also between two nonmetals, usually, but not always. Usually those are going to be two of the same nonmetals, so like a diatomic situation, where you have equal sharing of electrons and electronegativity difference of 0. So again, just kind of reviewing what's going on here. Polar covalent bonding, one atom pulls on the shared electrons with greater force than the other. I'm going to add in here, due to difference in electronegativity. There. Scoot that in. And this results in what are known as dipoles being formed, molecules that have areas of positive charge and areas of negative charge. Atoms that share electrons equal with equal force, like your diatomic elements, and this might be a good place just to remind you. I can't type this morning. There we go. Hinkelbroth, right? Hydrogen, iodine, nitrogen, chlorine, bromine, oxygen, and fluorine are our 7 diatomic elements, things that bond to themselves, right? Yeah. So I think we're going to call it a day. 10 minutes. Look at that. When I see you in class again, we're going to be doing more work with polar versus non-polar covalent bonds. Yeah, if you have any questions, let me know. Other than that, I'm going to talk to you in a little bit. Bye.